Välkomna till Kungliga Vetenskapsakademin och den här presskonferensen när vi ska presentera årets Nobelpris i fysik. Welcome to the Royal Swedish Academy of Sciences and this press conference when we will announce this year's Nobel Prize in Physics. We will keep to our tradition and begin the presentation in Swedish and then continue in English. You are, of course, later on welcome to ask questions in either of these languages. Jag heter Hans Ellegren, jag är ständig sekreterare här på Kungliga Vetenskapsakademin. Till höger om mig här sitter professor Eva Olsson som är ledamot av Nobelkommittén i fysik. Och till vänster professor Tors Hans Hansson, också ledamot av Nobelkommittén i fysik och sakkunnig inom ämnet. My name is Hans Ellegren. I'm the Secretary General of the Royal Swedish Academy of Sciences. And to my right is Professor Eva Olsson, member of the Nobel Committee in Physics. And to my left, Professor Tors Hans Hansson, also member of the Nobel Committee in Physics and expert in this field. Årets pris handlar om kvantmekanikens kraft. This year's prize is about the power of quantum mechanics. Kungliga Vetenskapsakademin har idag på morgonen beslutat att utdela 2022 års Nobelpris i fysik i lika delar till Alain Aspect, Université Paris-Saclay och École Polytechnique Palaiseau, Frankrike. Till John F. Clauser, J.F. Clauser and Associates, Walnut Creek, Kalifornien, USA. Och till Anton Zeilinger, Universitet Wien, Österrike. Det tilldelas priset för experiment med sammanflätande fotoner som påvisat brott mot Bell-olikheter och banat väg för kvantinformationsvetenskap. The Royal Swedish Academy of Sciences has this morning decided to award the 2022 Nobel Prize in Physics in equal share to Alain Aspect, Université Paris-Saclay, and École Polytechnique Palaiseau, France. John F. Clauser, J.F. Clauser and Associates, Walnut Creek, California, USA. And to Anton Zeilinger, University of Vienna, Austria. They received the prize for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Professor Olsson will now give us a short summary, please.
Thank you. So, quantum information science is a vibrant and rapidly developing field. It has broad and potential implications in areas such as secure information transfer, quantum computing, and sensing technology. Its origin can be traced to that of quantum mechanics. Its predictions have opened doors to another world, and it has also shaken the very foundations of how we interpret measurements. What today is considered logical, measurable, and quantifiable was initially debated by Niels Bohr and Albert Einstein in philosophical terms. John Bell transformed the philosophical debate into science and provided testable predictions that launched experimental work. This year's Nobel Prize in Physics honors the groundbreaking work and science of the central figures Alain Aspect, John Clauser, and Anton Zeilinger, who took up the challenges of Bell and tackled them in the laboratories. Professor Tors Hans Hansson will present the details of the work. Thank you.
Thank you, Professor Olsson. And I'll leave the word to Professor Tors Hans Hansson for a more detailed presentation.
Thank you, Eva. introduction. Einstein, in a letter to a colleague, famously wrote, "I'm convinced that he," and he meant God, "does not play dice." And what did he mean with this? Quantum mechanics, the theory of atoms and light, had been immensely successful, but it was also very weird. For instance, take the simplest atom, hydrogen, just one electron moving around a proton. Quantum mechanics couldn't even tell you where the electron was, just the probability to find it somewhere. Einstein didn't like that. He thought that a good theory should give you precise predictions, just as Newton's theory tells you exactly where the moon is in its orbit around the Earth at every moment. Not everybody agreed. Here are two of the founding fathers of quantum mechanics, Niels Bohr and Edwin Schrödinger. They thought that quantum mechanics was okay as it was, didn't need anything more, you just have to accept the peculiarities. And this position was put very clearly in this paper written in 1935 by Edwin Schrödinger. It was an answer to a paper written earlier that year by Einstein, Boris Podolsky, and Nathan Rosen. And they had come up with the thought experiments, which they thought proved, demonstrated that quantum mechanics couldn't be the full story. And now I will explain to you a modern version of that experiment. So here you see a source. This source emits pairs of particles, entangled pairs, Bell pairs. We'll come back to that concept. And they reach Alice and Bob, who makes measurement. They measure a property of these particles that is called spin. And in quantum mechanics, this spin can only take two values, plus or minus. So what happens when you do it many times? Alice will see a sequence of pluses and minuses, plus, minus, plus, plus, minus, minus, plus, etc. Looks completely random. And the same is true for Bob. But the strange thing is that when they compare the measurements, every time Alice sees a plus, Bob will see a minus, and vice versa. And that's very strange, because they are far away from each other, and these particles look exactly the same. Well, perhaps, let's look at it. Here we have the quantum cards. They look all the same, huh? We shuffle them or entangle them, and then here they go. And they can answer questions on signs. What sign do you have? Plus? What sign do you have? Minus. Okay? Let's take another set of quantum cards. Here they go. What sign? Plus. What sign? Minus. Strange. They look the same. How could they know what sign they have? Well, you see, here it is a trick. That is the following thing. Look, that was a minus, and that was a plus. So each entangled pair had one plus and one minus. I don't know where the minus went there or there, but it was always one plus and one minus. So, could it be that quantum mechanics was the same? Could it be that there were hidden informations like on the cards? Could it be that nature was a trickster? Okay, just like I was before. Perhaps quantum mechanics is not complete. Perhaps there is something hidden. Einstein would have liked that. And it's a very natural way to think that it would be like that. But years went on, decades went on. No one found such a theory that could explain the experiments with such hidden variables. So this became something more of a philosophical question. Most physicists didn't care very much until in 1964, John Bell made an amazing theoretical discovery. By looking at a variation of this experiment that I just told you about, he could show that in that case, the predictions of quantum mechanics couldn't be reproduced by any kind of theory based on hidden variables, however complicated. And when you think of it, that's really strange, because that means that when you measure on one of these particles, it's not so that you just reveal a property that is already there and measure. No, the quantum information about the state is in the full entangled state of both particles. Indeed, very strange. And so thought the young John Clauser, who said, let's do Bell's experiment. Let's perform it in the lab. Perhaps quantum mechanics isn't right in that situation. Now, that was easy to say, not so easy to do, because with the existing lab equipment, you couldn't perform that experiment. But with collaborators, he came up with a variation of the experiment that could be performed, and he and the late Stuart Friedman went to the lab. They did it, and they found that quantum mechanics works also in this case. Now, there were loopholes. And one particular loophole that John Bell had been very concerned about was that of locality. That means that Alice shouldn't be able to send signals to Bob so they could sort of agree on the result of the measurements. And that was hard to exclude experimentally. But in 1976, Alain Aspect wrote a paper where he proposed such an experiment. And a couple of years later, went to the lab, performed the experiments, and guess, again, quantum mechanics rules. So why is this a big deal? Didn't we know that quantum mechanics works? Well, to explain to you why it's such a big deal, let's go back again to 1935. Here is another paper by Schrödinger, which he says, I would not call entanglement one, but rather the trait of quantum mechanics. So now, much later, in retrospect, we understand that in addition to the profound philosophical and foundational implications of the studies of Bell states, the experiments performed by Clauser and Aspect opened the eyes of the physics community to the depth of Schrödinger's statement and provided tools for creating and manipulating and measuring states of particles that were entangled, although they were far away. And physicists now started to understand that entanglement and Bell pairs is a quantum resource that you can use to achieve amazing new things. And it's no time here to even start to tell you that story. I will just give you one example, which is picked because it illustrates one of the many groundbreaking contributions by the third of this year's laureates, Anton Zeilinger. So to understand this, you have to know that a goal of a quantum mechanics today is to build a quantum network. What is that? A quantum network is a series of nodes, and these nodes should be able to communicate via quantum entanglement. In these nodes, you can have quantum devices like encryption devices. How do you build such a network? It's difficult because entanglement is brittle. If you send it to an optical fiber, it very easily gets destroyed. So you need some new trick. And just an amplifier won't work because amplifiers destroy entanglement. So here is the trick, the method that Anton Zeilinger came up with. It's called entanglement swapping. You have two of these Bell pairs, like this. One of the particles here, one, and the other 4 goes far away from each other. The 2 other comes together. Here, you make a measurement, so you entangle particle 2 and 3. And then magically, 1 and 4 becomes entangled, although they had never been close to each other. It's wonderful. So now you can think of doing it in a chain. You do 1, you could do another, you do a third, etc., and you can build up a network. Another method to get long-range entanglement is not to use optical fibers, but to send just light through the air. And I'll just give you one spectacular example of this. And that was in 2018. There was an intercontinental quantum link set up using the Chinese MICUS quantum satellites between the group of Jianwei Pan, the Academy of Science in China, and with Anton Zeilinger's group in Austria, over 7,600 kilometers. Pretty amazing. And now we are at the forefront of current research, and I will just end with a few comments. So today we honor 3 physicists whose pioneering experiments showed us that the strange world of entanglement and Bell pairs is not just the micro world of atoms, and certainly not the virtual world of science fiction or mysticism, but it's the real world that we all live in. And researchers now, all over the world, they use entanglement and Bell pairs, both in curiosity-driven fundamental research and in utility-driven applications such as quantum cryptography or quantum computing. Thank you for listening.
Thank you, Professor Hansson. Now we shall see if we may have one of the laureates with us. Professor Anton Zeilinger, are you there?
Yes, I'm here.
Good morning, Professor Zeilinger. Please accept our warmest congratulations to receiving the Nobel Prize in Physics.
Thank you very much. It was very kind to receive your phone call just about an hour ago. And I'm still kind of shocked, but it's a very positive shock. Thank you very much.
So were you surprised to get the call?
Yes, I was actually very surprised to get the call. Thank you.
Yeah. I'm sitting here in the session hall of the Royal Swedish Academy of Sciences, and we are at the press conference live here. There are many interested journalists from the international press as well as from Sweden. Would you be ready to take some questions from them?
With pleasure, yes. But I don't understand Swedish, but anyway.
I'm sure they will ask in English at least. Questions?
Right.
SVT?
Hallo, Professor Zeilinger. Glückwünsche, herzliche Glückwünsche. Congratulations. This is Swedish television. I'm curious, could you say something? We can read in the paper here that you demonstrated quantum teleportation, which does sound like something absolutely impossible. Could you say something how it is possible?
Yes. Actually, quantum teleportation uses the features of entanglement. It is not like in the Star Trek films or whatever, transporting something, certainly not a person, over some distance, but the point is using entanglement. You can transfer all the information which is carried by an object over to some other place where the object is so to speak, reconstituted. And this is done, and that is actually the surprising feature. You can transfer the information without knowing the information, because to know the information would violate Heisenberg's uncertainty principle. So far, this has only done with very small particles, and it is certainly absolutely impossible to think of very large objects. but it's fundamentally important for transferring information, maybe between quantum computers.
Okay, we have several hands raised here. Was there one here, please?
Yeah, hi, Anton, this is Nordic Chinese Times. First, congratulations on getting this year's Nobel Prize in Physics. Can you kindly share with us what inspired you of the idea of this topic, and to what extent will the work influence the future of the quantum physics or even science in general?
Thank you very much for that question. I have to say that I was always interested in quantum mechanics from the very first moments when I heard about it. And I was actually struck by some of the theoretical predictions, because they did not fit, the usual intuition which one might have. So I was lucky to work in Vienna with my supervisor Helmut Rauch, who was a pioneer in quantum physics, and he provided the freedom to do these experiments, which at that time were completely philosophical, without any possible use or application. And this has changed now, as it has been mentioned. There are possible applications discussed and also implemented in laboratories. The interesting point is that some of the fundamental questions, the very question, what does this really mean in a basic way, are still unanswered in my eyes, and that is an avenue for new research.
Thanks so much for sharing.
Yeah, one question there at the back.
David Keaton from the Associated Press. Congratulations, Professor. First of all, I'd like to ask, what, in your opinion, signifies this prize for the field in general of quantum mechanics? What does it mean for this field of research, do you believe? And second of all, in 2022 today, what excites you the most in this field? What areas do you think are going to be yielding the most new discoveries, both theoretical but also maybe practical? Thank you.
Well, I guess that this prize is an encouragement to young people, and I would mention here that the prize would not be possible without more than 100 young people who worked with me over the years and made all this possible, because I alone could not have achieved this. That is quite clear. So I look at it as an encouragement, particularly for young people. My advice would be, do what you find interesting, and don't care too much about possible applications. On the other hand, I understand this recognition is very important for the future development of possible applications, and this is going to be quite interesting. I'm curious what we will see in the next 10 or 20 years. That is, in my eyes, this is absolutely quite open. On the foundations, the fundamental thing, the issues about reality and the role of space-time in a very fundamental way is still not answered, and I expect some interesting experiments there in the coming years.
Okay, we have more question here, please.
Congratulations, Professor Zeilinger. So this is Yu speaking from Geneva Observatory. So my question is, what happens if we send an entangled particle into a black hole? Do we still get information from it? Thanks.
Oh, this is a very basic question about the nature of black holes and what happens there. I should say I'm not a specialist for that. I'm more. That last year there was there were prizes for black holes. Also, there is a black hole in the center of the universe, and probably Professor Kensler and Professor Penrose can better. I have a naive idea, and my naive idea is that I think information cannot be lost forever. But that is just my personal opinion.
Yes, please.
Anneli Megner-Arn, Swedish TV4. Congratulations on the prize. I would like to fill in Thomas von Heine's question from SVT. And when you were talking about teleportation, when I think of teleportation, I think teleportation of mass, like a person is jumping from here to there in different galaxies. But you said teleportation of information only. Is that correct? So there is no mass involved here?
Well, actually, this is a very good question, actually. I like that. The point is actually that it does not matter which mass something is composed of. For example, if I exchange all the carbon atoms in my body with the carbon atoms in somebody else's body, I'm still the person. It doesn't matter. Important is the information. Important is how is the object constituted? How are all these constituents arranged together? And that is what defines individuality and so on, not the matter of which we.
So you mean that in the very, very future, like maybe 10,000 years from now, you might be able not to actually jump to another galaxy, but have yourself building up again from different material at another place, like the same that we are sending TV now, for instance, that you get.
Well,
yes.
Well, at first, I might say that I don't think that I will experience anything in 10,000 years. But that's a different question. The teleportation of people is today. It's the same kind of science fiction as it always was. So this is just science fiction, and it is not, in my eyes, it is not a question of science.
Okay, obviously a very exciting topic with an exciting last question here. I think this was the last question from the press to you, Professor Zeilinger. Thank you, and once again, our warmest congratulations for receiving the Nobel Prize in Physics. We look forward to meet you here in Stockholm in December at the Nobel Prize ceremony. See you then, Professor Zeilinger.
Thank you very much again.
Yeah, bye-bye. Okay, let's move on to more questions about the Nobel Prize in Physics, about the research, about the work of the committee, etc. Please, in either language, Swedish or English. No questions. There's one here, please. Yes.
Yes, hello. My name is Linda Norstedt. I'm from the technology newspaper Ny Teknik. I wonder if you could tell us a little bit about why you chose these three. Why is this knowledge worth the prize?
Professor Hansson?
Well, in my presentation, I try to make clear what the three laureates did. And I should add, and I think I sort of alluded to that in my explanation, that, of course, Professor Zeilinger has also made a number of other groundbreaking contributions to the further development. But when looking at the complete field that started, that was initiated by these groundbreaking experiments, the committee found that it would be wrong to just pick some of the very spectacular elements that has appeared lately, like teleportation, you know. It's something that really makes headlines. But we wanted to go back